Okay, this video we're going to talk about how to measure capacitors and inductors using your oscilloscope and just a handful of parts. The video was inspired by a blog post by Glenn Chenier on the scopejunction.com website, and basically he just showed this basic principle, and pretty simple thing, and I thought it would be a great video because it does a couple of things. It shows us how to use some very basic circuits like a simple RC circuit or an LC tank circuit to measure and calculate out values of unknown capacitors and inductors. It also shows a useful way to use an oscilloscope in the lab, and it also shows us how we can use another circuit that I did a video on here not too long ago. This fast edge pulse generator that's based on a Schmitt trigger oscillator and a couple of parallel buffers. I did a video on this to show how to use this circuit as a TDR. And so we can now use this as a source for measuring capacitors and inductors. And the principle here is that we will basically put our unknown capacitor here through with a known resistor, hit it with this rising edge, and measure the response. And by doing that, we can calculate out the capacitance value. Similarly, for the inductors, we'll basically form a tank circuit with a known capacitor and our unknown inductor. Okay, and then hit that with the high frequency content of this edge, and this circuit will ring at its resonant frequency. Knowing the resonant frequency and this capacitor value, we can calculate out the inductor. So let's take a look at what the circuit actually looks like and then how I built it. So the fixture is basically this circuit right here. Okay, we've got our input here is a BNC connector. The first part of it to measure the unknown capacitance is a simple resistor. I chose 1 ohm. You can use something else, but 1 ohm works out just fine for the frequency of the circuit that I'm dealing with. And then we put our unknown capacitor here. So we basically take our fast edge coming in here, and we measure the response of across the capacitor, and it would kind of look like this. Here's our fast input, okay, and then the output is going to have this exponential, rise or fall time. Now, without going through all of the math of it, the simple fact of the matter is that this exponential rise is going to reach 63% of its final value over a time period that's equal to the product of the resistor times the capacitor. Okay, so it's a pretty simple thing. And to make life even easier, if we adjust our scope so that this signal from top to bottom occupies 8 divisions on the scope screen, okay, 63% of 8 is 5. So all we need to do is measure how long it takes to go from baseline up 5 divisions out of 8. So now we've measured that time period. Once we know that, we can calculate the capacitor very simply by taking that value divided by R. Okay. On the unknown inductor side of things, we basically form a LC tank circuit. Now the LC tank circuit is going to have a high impedance only at its resonant frequency, and a low impedance on either side of that in terms of frequency. So when we hit it with some high frequency energy coming through this differentiating cap here, the circuit's going to ring. So each of these edges is going to result in a ring, kind of like ringing a bell. Okay, all we need to do is measure that frequency. So we can basically rearrange the formula for resonance of an LC tank circuit, which is this, down to this here. So if we know, we measured the frequency, we know the capacitor value, we plug them into this equation, and we can calculate out the inductor. So let's take a look at how this circuit was built. Here's the fixture here. I have it bolted onto our fast edge pulse generator. That's this circuit here. You may remember from the previous video on doing the TDR. Okay, and I've got that connected up with just a little BNC coupler here to this new fixture. So the fixture is set up where this point right here is ground. This point is the connection for the tank circuit. That's our 10 picofarad coupling capacitor. Okay, so that is this port, this part of the circuit right here. This port right here is for the connection for the unknown capacitor right here. So if we look underneath this, you can see there's my 1K resistor. That's connecting up to that black set of connections. Let me rotate this around a little more. You can see this connection here is going down to that capacitor. Okay, and then the other end of that capacitor connects up to this top terminal strip. So I got both of those things kind of built right on here. So let's go make a measurement and show how it works. So let's start off with our unknown capacitor. I mean, in this case I kind of know what it is, but we'll pretend we don't. And if we stick that in our circuit here, okay, push that in, okay, and grab my scope probe and connect up ground and connect up our probe to our capacitor connection there, and we go look at the scope here. There's our square wave. Now all we need to do is go adjust that to kind of be full 8 divisions here. So I'm just going to use my variable adjustment here and adjust that to be kind of top to bottom of the screen, because that's 8 divisions on the scope screen. And now we just need to zoom in on the edge to measure the rising edge. You could use the 10x multiplier and adjust the position. I like using the delayed time base. So if I pull on the horizontal control knob here, I can adjust the sweep speed of the secondary time base, okay, and adjust its position. So now I can actually see that rising edge. Let me go one more click here, it'll probably be good. I can move that position, and then if I push the knob in here, I'll go just to that delayed time base, and now I get just that rising edge, okay. And what I'll do is I'll adjust its position so that that rising edge is just starting right at 1 gradical. It makes it easy to make a measurement. And I'll put my delta T cursors on here and adjust one of the cursors to be at that gradical where we're starting, and adjust the other one to right where that signal is crossing the 5th division. Okay, and it looks like it's right about here. And if we look at the delta T there, it looks like about just over a microsecond, so 1051 nanoseconds. And if we take a look at the equation here, if I know that that time is 1,000 microseconds, or excuse me, 1,000 nanoseconds, or 1 microsecond, I know the resistor is 1,000 ohms, that means the capacitor is 1,000 picofarads, or 1 nanofarad, and that indeed is what it is. If we can focus in on that, maybe it says 1N on it. Okay, so that's how we measure the capacitors. Now if we want to measure an unknown inductor, let's just say this is our known capacitor of 1 nanofarad. So we'll stick that in the fixture here. Just have to do this with one hand and hold the camera. And let's take my quote-unquote unknown inductor here and stick that across here as well. And now I'll stick my probe in here to measure the response of that circuit. Okay, and I'm going to bring my scope back to, I need to kind of crank the sensitivity up here because the circuit is going to load that signal down quite a bit. So I'll go down to say 20 millivolts a division, crank up the speed here, and now I can actually see that ringing going on. Okay, and in this case we'll just use the times 10 mag and move our position over and take a look at what that signal looks like. And if I turn on my cursors to measure frequency, let me adjust the position here so I'm kind of centered around baseline, and I'll go measure 1 cycle here, and that 1 cycle is about 2.73 megahertz. So I know that the resonant frequency of this LC circuit is 2.73 megahertz. So we just need to kind of plug those values into the calculator here. So I know I've got 2 and pi, multiply those together, 2.73 megahertz, and multiply that. I'll square that, multiply by our known capacitor, which is 1 nanofarad, and take the inverse of that. And that says that that inductor is 3.4 microhenries. And that's pretty close to 3.4, 3.3 microhenries. And if we take a look, we can see some green bands on that inductor, so it's likely a 3.3 microhenry inductor. Of course, this process is only going to be accurate to within, probably 5 or 10%, but generally that's okay for making these measurements. So anyway, that's a pretty neat technique to use your scope to measure inductors and capacitors, and also get a dual use out of this fast edge pulse generator, which gives you another excuse for going to build that. Thanks again for watching, and I appreciate any comments and feedback you might have. Take care.